We are into our third lecture of friction now. So at this stage, we have learned the concepts related with friction, but a lot of different type of applications will come into play. And obviously, anything to do with friction will include the concept of free body diagram and the previous concepts that you've learned in Newton's laws. So we'll be doing a lot of questions in today's lecture and the next couple of lectures also, which you can treat those questions like it will simultaneously be a revision of all your concepts of Newton's laws of motion also, not just friction. So you can treat it all like one common chapter. So let's start with an example related to friction on an inclined plane that we discussed last time. So this time let's take a system with a pulley on an inclined plane, but the difference is now it's a rough inclined plane. In the chapter of Newton's laws of motion, any inclined plane we took was a smooth inclined plane. But now extending that to friction, so let's say this is a 30-degree incline, and just yeah, I'm putting it. Right, so we have this system now, but only difference is this will be a rough surface now. Okay, so 30-degree incline with two blocks A and B. Okay. Now this surface has a coefficient of friction which is 1 by √3 given to us. Okay. The coefficient of friction is given to us as 1 by √3 and angle of inclination is 30 degrees. Okay. So if mass of A is, let us say, 2 kilograms, whereas mass of B is 4 kg. So first of all, make free body diagrams of A and B and determine friction or frictional force on A in newtons. Okay, and tension in the string in newtons. Take G as 10. And secondly, calculate the acceleration. Of blocks A and B. So let's start with this question, people, and we'll discuss more questions as we go along. Okay, very good. So I think the friction on A will come out to be 10 newtons, if I'm not mistaken. Okay, so those of you getting that answer should be correct. Some people have got it to be different values, so just check your solution. So anyhow, I'm making the free body diagram first. Okay, so you will see that definitely B is heavier here. So there's no doubt that B tends to accelerate downwards. A will tend to accelerate, and there's a simple pulley system of single string. So there's no constraint relation complexity involved. There's the same magnitude of tension acting on both of them. So they will have the same magnitude of acceleration. So now it's just a matter of the free body diagrams, which will take the okay. So remember the mass of A is 2 kg. So I will directly show the components of weight in terms of the mass only. Okay, so this is 2g cos theta, and this is 2g sine theta. Okay, this is the tension which is dragging it along this direction with an acceleration E. Of course, there is normal reaction N. So because it's dragging in this direction, so इसपे kinetic friction कैसे act करेगा? The kinetic friction will be opposite to the direction of slipping. So the kinetic friction will be like this. Okay, and the kinetic friction on A will be equal to mu into N. So that's one equation. Okay, then of course we have T minus 2g sine theta minus kinetic friction is equal to 2a. Okay. This one equation, because mass of A we are taking as 2 kg. So with that thing, and of course theta also is 30 degrees. So we'll plug that in later. And we have normal reaction is equal to 2g cos theta. So that's our second equation. So from equation 2, you can see normal reaction is 20 into root 3 by 2, or 10 root 3 newtons. Okay, so kinetic friction will become mu n, so that will become 10 newtons because mu is 1 by root 3. Okay, so this is that answer also. Okay, now to solve for acceleration, we'll have to plug this in this equation. So equation 1 will now become t minus 10 minus 10 is equal to 2a, or t minus 20 is equal to 2a. This is the equation for the block A. Now on the other hand, the block B, that has a mass of 4 kg, has the same magnitude of acceleration downwards, tension T acting upwards, and a weight of 4g. Might have taken, some of you I think have made the mistake of taking the weight as 2g maybe. So don't forget the mass of B is 4 kg. Okay, so for B we have the equation 4g minus T is equal to 4a. So this will become 40 minus T is equal to 4a. This is the equation that we are getting for B. Now just add these two equations and you will get your answer. Do equation A plus equation B. So कितना जाएगा? 40 minus 20 is equal to 2 plus 4a. So 20 by 6. So the acceleration will come out to be 10 by 3, or 3.33 meters per second square. And the tension will come out to be okay. So some of you seem to have got these values wrong, so just check it out. Friction, many of you got this correct, 10 newtons. So those are our final answers, and these are the free body diagrams. So friction acting on A is 10 newtons. Tension in the spring is 80 by 3 or 26.67 approximately newtons. Okay. And what is acceleration? Is equal to 10 by 3 or 3.33 meters per second square. So these are the final answers, people. Make sure you're clear with this. Okay, very good. Now we will do a sort of a revision question, going back to a bit of Newton's laws application. We'll come back to all this friction and all later. Okay, or actually we can include friction also, no problem. Yeah, conceptually it is over, Tej, but it will take at least 2 or 3 more lectures to complete all the type of problems. Might have seen there are many problems in H.C. Verma. But concept wise it is over. Okay, so there is a spring like this, block like this. Okay, so given mass of the block is 10 kilograms and the spring constant is 20 newtons per centimeter. Okay, now initially the spring is relaxed, that is extension is 0 and the block is at rest. Okay, now we start applying a horizontal external force E equal to 0. Horizontal force of magnitude, let's say 50 newtons, starts acting on the block. So first of all, find its acceleration just after, that is, at the moment when the force starts acting. And secondly, find its acceleration at an instant when the displacement of the block equals to 1 centimeter. By the time the displacement of the block has become 1 centimeter. We'll include spring force also in the dynamics here. Okay, so needless to say, all you have to do is make free body diagrams for both of the situations. For both of the parts, you have to make individual free body diagrams. You have to just understand the action of the spring force. The spring force is always kx in magnitude and always opposes the change in length of the spring. So if you are stretching the spring by x, it will point back towards natural length position. If you're compressing the spring by x, it will point back, to the relaxed state of natural length. So please send me the answers, people. This is simple in the sense that you don't have to resolve forces or anything. All the forces are either vertical or horizontal, so it's pretty easy. Okay, very good. I'm getting a lot of correct answers. Many of you have sent the correct answers. So let's just work it out. So in the first part, what is happening? See, the spring is still in its natural length. The spring is still at its natural length. X is 0. So it does not apply any tension. Okay. So the only horizontal forces acting will be F, which is overcoming the maximum friction, and this is becoming kinetic friction, because we can see that the normal reaction, which is equal to the weight, is how much? It is 100 newtons. Okay. So maximum friction, which is mu n, is 20 newtons, and the force that we are applying is how much? It is 6. It's 50 newtons. So F is greater than maximum friction. So the block will slip. Okay, and the friction will become kinetic friction, which is again mu n. because here there's one common value of mu. So this common value of mu means that mu k is equal to mu s is equal to 0. Okay, so initially this is your free body diagram, and so we have F minus kinetic friction is equal to ma. This becomes our equation. So we have 50 minus the kinetic friction mu n, which will be 20 newtons, is equal to mass of the block into acceleration. So the acceleration in the first part is 3 meters per second square. And good to see many of you have got this correct. Okay. But now let's see what's happening in this part. The second part. So by the time you are coming to that situation, if the displacement of the block from this original position, this is where it was at t equal to 0. Now from here, if the block is getting displaced by x or by whatever 1 centimeter, okay. So whatever is the displacement of the block, that becomes the extension of the spring. No? So x is equal to the displacement of the block, which is 1 centimeter at that time. Okay. So now the spring has developed a tension. See, the spring has developed a tension which will be opposite to its extension. So it will be inwards, and that tension will be equal to kx. So it will be equal to this spring constant, which is 20 Newton per centimeter multiplied with 1 centimeter. So the tension in the spring will be 20 newtons. Okay. So for this one, when we make the free body diagram, there's one additional force. There is the spring force, which is 20 newtons, along with kinetic friction, which is also 20 newtons, and external force F, which is continuously 15 newtons, and rest of the things are not changing at all. So you can see the acceleration would have changed. Now the acceleration has become some A prime, let's say. So F minus kinetic friction minus spring force is equal to mass into new acceleration. So 50 minus 20 minus 20 is equal to 10. The acceleration is reduced to 1 meter per second square. A prime, this new acceleration is changed to 1 meter per second. Okay, so this part's answer I'm giving with a different symbol A prime, that is 1 meter per second square. So hope this is clear to all of you, and you've understood through this also how the spring comes into play. Yes, very good, Krish, that's correct. Yash, your answer is correct. अरे I'm saying just after we start applying the force, na beta, t equal to 0 पे force लगाना start किया ना. So this is when force starts acting. Na? So I'm showing you in the diagram that the force is already acting. Just at that moment, t equal to 0, when I start applying the force. No, velocity is 0, but acceleration is there. Na beta? That's why it starts moving. अगर acceleration 0 होता तो how will it start moving? Yeah, so yes, what is happening here is that when the motion starts, its initial velocity is 0, but it starts with an acceleration of 3 meters per second square. So it has a rate of change of velocity, dv by dt is equal to 3. So at some time, So this is at t equal to 0, but at some very short time later, t equal to dt, उसपे क्या हो जाएगा, उसका velocity will become 3 dt. So imagine this is like a microsecond or something. So it will become 3 millimeters per second at that instant, the velocity. Okay, so hope this is clear with my numerical example. But now this is a situation where what is happening, it's not moving with uniform acceleration. As you can see, as the spring is stretching, the acceleration is reducing. So it started from 3, but by the time you're having a displacement of just about 1 centimeter, the acceleration has reduced to 1 meter per second square. Okay, so this is another interesting aspect of it, which we will see in the next chapter after friction, which is work energy. Okay, but we have lots of things to cover in friction before we come to that. Okay, next example, let's pick up. Now we are coming to slightly trickier questions, but very typical of friction, those type of questions. And typical of this chapter. So we have two blocks, A and B, like this. This surface is smooth, but this surface has a coefficient of friction equal to 0.4. Let's say this is a rough surface. And then we have another block of mass of C attached over here. Okay? And this is in a vertical situation, G is equal to 10 meters per second square. Now, given that mass of A is 5 kilograms, mass of B is 15 kilograms. Okay. So first part, we find the maximum possible value of mass of C for which the system can remain in equilibrium. Okay, that's the first thing. And the second part, instead of that, suppose if mass of C were to be equal to 10 kg, then find the acceleration of A, acceleration of B, and acceleration of C, if any, when the system is released from rest, okay, with the thread taut. Okay. So very carefully make the free body diagrams of all the three blocks first, and then try to understand how we can work out. First of all, the situation where we are finding like the maximum mass of C, so that the friction between the block B and the floor is able to keep the system at rest. Okay. Then we'll come to the next part. Just give me a moment. Yeah, so how much is the answer for the first part coming, people? Nobody got the answer? Yes, Yash and Vashist, very good, correct. Yes, Jash Upadhyay, your answer is not correct, but just check your calculation. Both the Yashes and Vashist, your answer is correct. Tej, no, that's not correct, unfortunately. For the first part, at least, it's not correct. Krish, correct. So just give you the answer. First part answer should be 8 kg. Mass of C should be less than equal to 8 kg for system to be at rest. So maximum is 8 kg. Acha, sorry, Jash. You gave the answer 8 kg. Yeah. Why? I'm seeing the answer for something else here. No, just you given the answer is one. Acha. First is 8 kg. Okay, I thought you wrote the answer 1.8 kg. First part, the answer is 8 kg. Okay, that's correct. Yeah. Okay, so hope all of you got the first part. Okay, I'll just quickly make the free body diagrams for the first part, then we'll come for the second one. Now, one thing you have to understand in the second one, not all the blocks will have acceleration. You have to be very careful because there is no friction between A and B. So be careful before you say that all the blocks will have acceleration. Huh? So anyway, in the first part, for equilibrium, okay, so let's say this is the block A, this is the block B, and below here somewhere this is the block C. So now let's figure out all the forces. weight, normal reaction. Okay. Same normal reaction he is applying on this below. Then this one's own weight, this one's normal reaction with the ground. The string pulling it with some tension and static friction acting from here. Same tension on this side and weight of this block. Okay. All of them are at rest. Okay. So acceleration of this is also 0. Acceleration of this obviously is 0. Acceleration of this is also 0. So let's start with all this. Okay. Then weight of E, which is 50 newtons. Normal reaction, let's say N1. Normal reaction N1. Then weight of B, which is 150 newtons. Okay. And N2. And weight of C, which we don't know. You have to calculate. Okay. So these are the various forces. I'll just answer your question. Just give me a moment. Okay, let me complete with this Yakrish. Okay, so now you can see that the friction that is acting on B, it's acting between the ground and this. So the important normal reaction will be N2. Okay, so important thing to understand here that the friction's maximum value will be mu into N2 because N2 is the normal reaction at the ground. Okay, so now starting with this, you can see N1 is equal to weight of A. So that is 50 newtons. Okay, N2 is equal to N1 plus weight of B. So that will become 50 plus 150 or 200 newtons. Okay, so put that back here and we understand that friction's maximum possible value is 0.4 into 200. So that is 80 newtons. So now for equilibrium, for A to be 0, tension must be equal to static friction. So connect this here and this tells that tension should be less than equal to 80 newtons. And for this one, you can see that tension needs to be equal to the weight. Okay, so put this here now and you can see that the weight needs to be less than equal to 80 newtons. So this tells me that the mass of C should not exceed 8 kgs for equilibrium. Okay, now this will give you enough hint what happens when the mass is becoming 10 kg. When the mass is becoming 10 kg in the second part, the tension is becoming more than 80. Okay, so this has to slide, but be careful A doesn't slide because there's no horizontal force on A because this surface is smooth. It's only the ground which is rough. So keep that in mind when you're solving the second part. Okay, you'll get the answer. It's pretty easy. Yeah, you can do that also, Krish. You can make the free body diagram of A in non-inertial frame. But is that completely necessary? Now, just think about that also. It's not maybe necessary. You can look at what's happening to A in the ground frame also. Because here we are not asked to find the acceleration of A with respect to B or something like that. So it's not compulsory that you have to see non-inertial frame. You can keep things simple and just see it in the ground frame only. Na? You're following, Krish? Okay. So try it in the ground frame. Na? It will be easier to start with. We will continue about the relationship. Okay, I'll just verify the answer for you for this part. So B and C will have acceleration, whereas initially when the sliding just starts, A will not have acceleration. That's correct, Kunal. Of course, then A will eventually topple over, but just at the moment when you release it, now A will not have any acceleration. That's correct. Very good. So what will happen is B and C will have the same magnitude of acceleration, which will be T divided by, yeah, it's coming 0.8. Are you getting the acceleration 0.8? Anyone? Kunal, you are getting it. Yeah, 4 by 5 dt. That's correct. Very good. So the second part, you should be getting the acceleration as 4 by 5 or same thing as 0.8. Show you why that's happening. So more or less the same free body diagram, just that the values are changing, and that's why acceleration is coming into the picture. So this acceleration will be 0, but this one won't be 0. This one won't be 0. So you can see at the moment when you just release the system from rest now, A is sitting on top of B and B does not put any friction on A because that surface is smooth. So it doesn't apply any friction on A. So A does not move. So acceleration of A will be 0. N1 is just equal to weight and all that. So that's all that is same. N2 is 200 newtons. Okay. But the other thing is now this will change from kinetic to, static to kinetic friction. So this will become equal to kinetic friction, which is mu N2. So that is 80 newtons, as we saw. Okay, very good. So many of you have sent the correct answer now. It's 0.8 or this thing. So this equation, now, this will become 10 Newton. So 100 minus tension is equal to 10A. So that's our first equation. This is from C's free body diagram. Now from B's free body diagram, you can see tension minus kinetic friction is mass of B into A. So this will become T minus kinetic friction. Here we have picked up, it's 80 Newtons. So we'll plug in this value here. So that should be equal to mass of B, which was 15 kg. So 15A. Okay. And as far as A is concerned, its acceleration is 0. We can see for A what is happening. There is no horizontal force. Fx is 0. And along the y-axis, the forces are balanced. So N1 minus weight, that's also 0 like this. Huh? So now all we have to do is add the two equations. So once you understand how much and where the friction is acting, rest of the solving is just like your normal Newton's laws problem. So here you will get the acceleration as 0.8 meters per second square. Now you'll also realize this is just for a moment, because what will happen is next, after this starts moving very quickly, because the acceleration is considerably large, so very quickly something like this will happen, and this will topple over. Yes, okay. And the moment this falls over, now the friction will become less. So again, the acceleration will change. Okay, but we are not worried about that. No, we're not really concerned with that. So this is initial moment. Initially, when the motion starts. Okay, so this is the picture here. Okay, so hope this is 100% clear. नहीं 20A नहीं है बेटा, because B का मास कितना है यश? B का मास तो सिर्फ 15 kg है ना, वो A का मास है, but A is not moving along with B ना. You have to understand this. A's acceleration is 0. Just give me a moment. Yeah. So B's mass is 15 kg. It's A's mass which is 5 kg. But it's not this combined mass which is moving. Na? This point is very important here. It's A's acceleration is 0, but C's acceleration is A downwards and B's acceleration is A horizontally like this. Is the point clear, Yash? Yash Bhaviskar, that is, yeah. Okay, so that's a common mistake which you have to avoid. Practice enough questions and you will get used to these things. Okay. Okay, very good. Now I will okay, now what I also want to do is a couple of questions from the previous chapter, Newton's laws, which I want to discuss as doubts also. So a couple of questions from HC Verma. I'll just put up the question. So I think one of them is a question which Diti has asked. So this is an example from HCV. Newton's laws of motion chapter. Okay, so I'll just tell you the question number also. Just give me a moment. So in that, what is happening is you have this elevator box kind of thing. And there's like a hole in the box through which you connect a rope like this. And that rope is going around a pulley like this. And the other side of the rope is in fact also connected to the elevator itself. Okay. So this is fixed here, whereas the pulley is fixed to a ceiling here. Okay. So this is fastened here, whereas through this hole, a person inside is holding this. So the first part of the question is like this, that the mass of the box is given to us, the mass of the person is given to us, and we have to find, now he's also standing on a weighing machine. Okay, so this is a weighing machine. So if I'm not mistaken, I have to check the book again, but this is, I think, 40 kilograms and this is 60 kilograms or something like this. Okay. So in the first part, if the elevator, oh sorry, if the box plus person are stationary, okay, then find the reading in the weighing machine. Okay. And second part, find how much force the person should pull the box with so that the weighing machine shows the correct weight. True weight. Okay. It shows 60 G weight. So this is an example from H.C. Verma, Newton's laws of motion chapter. So we'll discuss this next. So I'll tell you the hint for, obviously for this part, you make FBD of the person, okay, and the box separately, and both of them are at acceleration equal to 0. So you'll get the condition. Now whatever is the normal reaction N on the person, okay, applied by the floor, which is basically the weighing machine. The floor on which he is standing is the weighing machine's floor, no? So that normal reaction will be the reading of the weighing machine. Okay, Diti, is this concept clear, beta? Okay, okay. And what about the second part? Have you got the second part also? Just make a correction. The box weighs 30 kg. Instead of 40 kg, make it 30 kg. Okay, so we'll discuss the second part. So obviously in the first part, you would have seen that the reading will be less than the true weight. Okay, when he is applying that much force that the system is at rest, the reading is less than the true weight. No? So then how would he, how would he change the system so that the reading is equal to the true weight? You would have to apply extra amount of force compared to the first part. So the moment he applies extra force, what will happen? The tension has increased. So the system will start, yeah, Krish, that's correct. Whatever force he applies, that is the tension. But in the first part, he's just applying that much force and tension so that the system is at rest. In the second part, he'll have to apply a larger amount of force and therefore the tension will be more. So the whole system will have vertical acceleration. In the first part, the system is in equilibrium. In the second part, you'll have to consider that the system has vertical acceleration. Okay, so let's figure out this question. So for the first part, you can see the system is in equilibrium, so it's pretty easy. So before you start all that, one thing you have to understand is that if he is pulling the rope down by applying a force F on it, that becomes equal to the tension in the rope. Okay, so whatever force he is applying is equal to the tension in both the parts. Whatever downward pulling force he applies, that becomes equal to the tension of the rope. Okay, I will just verify the answer. Just give me a moment. Okay, so in the first part, he is at rest. Okay, and the box is also at rest. Now on his body, the forces acting are the rope, a weight which is 600 newtons. Okay, and the floor is applying a normal reaction N. So T plus N is equal to mass of the person into G, or 600 newtons. And on the box, normal reaction acting, tension acting, and its own weight. So N plus weight of the box has to be equal to tension. So N plus 300 newtons is equal to T. So this is your second equation. So now we have to just solve for N. So solving for N. Okay, so from these two, tension, which is 600 minus N in this part, is equal to 300 plus N in this part. So the normal reaction will come out to be 300 by 2, or 150 newtons, and the tension will come out to be 450 newtons. Okay, so the weighing machine reads a mass of N divided by G, so 15 kg. So it misreads his mass by as much as, 1/4 of what it truly is. His mass is actually 60 kg, but it reads it only as 15 kg. So this is clear to all of you. Okay, now in the second part, what he's trying to do is the person has to apply a larger force, okay, so that the system accelerates upwards and normal reaction increases to 60 G, so that the reading of the weighing machine becomes 60 kg. Okay, so he will apply a larger force okay, so that he's pulling the rope down with a larger force, so the whole system is getting an upward acceleration of E. So now when you look at his free body diagram, it's having some upward acceleration E because of the combination of the new value of tension new value of normal reaction. So this is still 600 newtons, but we also want normal reaction here should be equal to 600 newtons. Okay. So T minus N plus the weight of the person is equal to mass of the person into E. This is our first equation. So this equation will now give us this thing, that T minus 600 plus 600 should be equal to 60E, or T minus 1200 should be equal to 60E. This is what we are getting from this. Whereas the box should have the same acceleration A upwards. On the box there is tension T acting, the same normal reaction downwards, and the weight of the box, which was 300 newtons. So for the box, what is happening? T minus N plus weight of the box should be equal to mass of the box into the same acceleration. That's our second equation. So this becomes T minus 600 plus 300 should be equal to 30E. So T minus 900 should be equal to 30E. So this is this equation. Okay. So from these two, we can find out that, for example, from the first one, 60E, if I divide it by 2, that becomes T minus 1200 by 2. And from this one, that's equal to T minus 900. That's 30. Okay, so this is equal to this one. So T minus 1200 is equal to 2T minus 1800. So T is equal to 1800 minus 1200. So the tension he has to apply has to become 600 newtons. Oh, wait a minute. I made a solving error here. No, that's fine. So the amount of force he will now apply will become equal to this tension, which will be 600 newtons. But notice something interesting. This will mean that the acceleration will become negative. When you substitute here or here, you can see that the acceleration will become how much now? Minus 10. It is not making sense. No, that is because there's some solving error probably. I'll just check it out. But why we have put the normal reaction equal to 600 newtons? Because it should read as true weight. I'll just make the corrections, whatever there is. Just give me a moment. So why we have replaced the normal reaction with 600 newtons here? This, because we want this thing, that this, for the reading to be 60 kg, okay, for that is his true weight, the normal reaction has to be equal to, oh, the mistake is here actually. This is not, this equation is wrong. Wait, this has to be 600 or 60 G. Understood now? That is the condition now, the second part. Okay, wait, that's why we are getting an odd answer. This equation only was wrong. N is upwards now here, not downwards. So for him, the equation is T plus N minus his weight, mass of the person, is equal to mass of the person into E. This is our first equation. So T plus 600 minus 600 is equal to 60E, or T is equal to 60E. This is what this equation gives us. When the normal reaction is equal to his true weight, this term should be 0. So directly T should be equal to mass into acceleration. Now we substitute that over here. Now this is fine because tension is acting upwards, these two are acting downwards. So tension minus 900 newtons has to be this. So solving these two, you will get 60A minus 900 is equal to 30A. So you will get A is equal to 900 by 30. So that's how much now? 3 meters per second square. So we should get acceleration as a positive quantity, and put that back over here. The tension should become 1800 newtons. So you'll have to apply a force which is as much as 3 times his weight to generate that kind of acceleration for the whole system, not just himself, but he's pulling the box also up with himself. So the force that he's applying will have to be 1800 newtons for N to be equal to 600 newtons. So the reading of the spring ball of the weighing machine to be his true weight, he'll have to put that much effort into it. He'll have to apply a downward force 3 times his weight. Okay, so make sure you understand this explanation I've given over here. Let me know if there's any doubt with this. I'll explain again. Okay, good. Okay. The last few problems of every exercise in HC Verma are always very interesting and tricky questions. Okay. So if you can get down to cracking those, or at least getting those with some basic hints, then you know that you have reached good level in that chapter. So very soon we'll be coming to the last few questions in friction chapter also in HC Verma. So E is not 30 ना, E कैसे 30 होगा? 30A is equal to 900. Oh right, A is equal to 30. Yeah, correct. Sorry, my mistake. So it's not 3, it's 3G or 30 meters per second square. Yeah. Anyhow, so hope this question is clear. Okay, so we'll finish up with one more question today. Now this is going to be a very important question from your understanding of friction point of view. Okay. So we are back to the case of the inclined plane. Now let's take angle of inclination as 37 degrees. Block of mass 5 kg is placed on it. Now this has a coefficient of friction equal to 0.5. Okay, and take g to be 10 meters per second square. Now we are applying a force like this parallel to the inclined plane on the block. So an external plane, an external force F is applied. Parallel to the inclined plane as shown. Okay. So first part, find the minimum magnitude of F to keep the block at rest. So what minimum force should we apply so that the block remains at rest? It should not move. That's what we're trying to find out here. Okay. And second part, minimum F so that the block starts slipping up the inclined plane. Okay. So just think very carefully when you make the free body diagrams about the direction of friction in each of these cases. It will teach you something important and interesting about friction. So make the free body diagram for each case, one when the block is held stationary by the force, and the other when the block is being pushed up the inclined plane. And then, get this limiting condition or this critical condition that, is just about enough to keep the block at rest, or just about enough in the second case to make the block start sliding. No, you will not need that much force. Okay. Yash and Krish, both of you, in the first case, the minimum force you require is just going to be 10 newtons. You will see 10 newtons is enough. But in this case, the minimum force that you need in the second case, that will increase now. Now in this case, it will increase to 50 newtons. Okay, so that's why I said you have to think little carefully why the two cases are different. एक में you're keeping it at rest. Okay. So I try to explain. You see, suppose you were not applying any force here, then what would have happened? The block would be sliding down. No? You know, it would be sliding down like this because mu is less than tan theta. Okay. So there would be kinetic friction acting like this. Mg sine theta, normal reaction, mg cos theta, all this. Okay. So the tendency to slip is downwards. So for the first part of the question now, when I'm preventing its tendency to slip downwards, I have to apply that kind of force which just balances this excess force na, in the first diagram. So मुझे उतना ही force लगाना है that I'm able to utilize static friction which is preventing it from slipping down the inclined plane. Okay, so if I'm applying force in such a way that it doesn't overcome mg sine theta, but it just provides enough so that static friction can help me overcome mg sine theta. So that the acceleration is 0. Okay. So F plus static friction is balancing mg sine theta. Normal reaction is balancing mg cos theta, and static friction should not exceed, cannot exceed mu n. Okay, so from your equation 1, you will see that F plus static friction has to be equal to 30 newtons. Okay, from your second equation, you will see that normal reaction is equal to 40 newtons. So now static friction, which is equal to 30 minus F, should not exceed mu n. So 30 minus F, which is the amount of friction we require, should not be larger than 0.5 into 40. So 30 minus F should be less than equal to 20. So that's why I said that F should be greater than equal to 10 newtons. Okay. So what that tells me is that in this diagram, in this situation, if I put F equal to 10 newtons, then for acceleration to be 0, the friction needed is exactly 20 newtons, which is equal to mu n. So this is the maximum friction available. Whereas if I apply a force of less than 10 newtons, then I need static friction of more than 20 newtons needed for A to be 0. But that is not available. So it will slip. That is not available. So this will not do. So I need a force of this. So understood, those who have got the answer of the first part of 50 newtons have you understood where you've gone wrong in the direction of friction. And yes, I think you made some calculation mistake. You got the answer is 15 newtons. Just check your calculations. Okay. So theta is 37 here, so and m is 5 kg. Now come to the second part. Now in the second part, the diagram is very similar, but the difference is that the block is now in a process of sliding upwards. So the moment it is sliding upwards, the friction has changed to kinetic friction. It has an upward acceleration tending to zero albeit, but it's still sliding upwards. So now, no matter what is happening, there is kinetic friction acting like this. Okay. So the whole thing changes because of that. Okay. So if I have an acceleration like this, I have the equation that F minus mg sine theta minus kinetic friction has to be equal to ma. And n is equal to mg cos theta. Kinetic friction is equal to mu n. Okay. So this equation here, this will become F minus this thing 30 minus, now kinetic friction from here will become 0.5 into mg cos theta, that is 0.5 into 40 or 20. This is equal to ma. So A being greater than 0, F has to be greater than 50 newtons. So just about 50 newtons is also fine. A is tending to 0, so F is tending to 50 newtons, just a slightly larger amount than 50, and it will start to slide upwards. So understood now? So we need a force of greater than 50 newtons for sliding up the inclined plane. Okay, so a force tending to 50 newtons, it just about starts to slide. At an acceleration tending to 0. So hope this is clear, the difference between the two cases. Okay, so this kind of logic is very important to develop in friction. Okay, now start working on problems from H.C. Verma. The first 20-25 questions you can now attempt in this week. Okay, and we will continue with discussions next week or whenever our next lecture is. I think we have a lecture on Sunday, is it? Yeah, Sunday. So we'll continue with more problems on friction on Sunday. So concept wise, we are done with friction, but as I said, it will take another couple of lectures at least to cover all the different types of questions. So anyhow, that's it for today, people. Thanks for attending. Wish you all the best.